The first set of environments and processes that we're going to talk about will be rivers, and there's a lot going on here. So moving water is one of the most important agents for shaping what we see at the surface of the planet. And specifically rivers and streams, so stream is just another name we use for river. Rivers and streams are one of the primary places where this happens. They're extremely important for erosion, transportation, and ultimately deposition of sediments. So we're going to take a look at some of these environments and basically look at a little bit at how rivers work, what's going on there. So let's start out with just some general terminology. And all this stuff is introduced in your book. I'm just going to highlight some stuff that I think is especially important or notable. First of all, the drainage basin. One of the things that we want to do is have kind of a manageable piece to look at. So we can't look at all the rivers at the same time. That's just too much. So one of the first things that we do is we pick a river. And if you pick a river, you pick a point on the river, and it could be the mouth of the river, so where that river empties into something else. Or if you want to, you can pick kind of an arbitrary point anywhere along the river. Everything upstream from that point is called the drainage basin to that point. So the drainage basin of an entire river, for example, if we want to talk about the Mississippi River, would be everything that provides water that comes out at New Orleans in Louisiana. They have a drainage basin. On this picture it says Gulf of Mexico. All the rivers that drain into the Gulf of Mexico, including the Rio Grande and the Mississippi, are highlighted in kind of a reddish color here. But within that, we can say, hey, there are a bunch of smaller drainage basins for individual rivers like the Ohio or the upper Mississippi or the Missouri, or the whole thing for the Mississippi would include all those tributaries. So there are a lot of different ways to cut it, and that's going to determine what kind of project you're working on, what kind of research you're doing. So here's an example with the Colorado River Drainage Basin. You can see on the right-hand side, we've got a map that just highlights the area that's drained. And then on the left, we have some more details. You can see some of the many tributaries. You can see that particular map is drawn to highlight the relief, so the changes in surface elevation. So there are many, many things that we might want to look at in a drainage basin. Some real basic things we could measure would be things like the area of the drainage basin, how long the river is, how long the river and all its tributaries are. We could also look at the total relief, the highest minus the lowest elevation. If we divide that total relief by the area, we get what's called a relief ratio, and it gives you an idea of the amount of elevation change for the area of the drainage basin. Another very important characteristic that we can look at in a drainage basin is the density of stream channels, or the density of tributary streams. The green picture on the right, or that map, does not look very dense because it's only showing some major rivers. If you look at the one on the left, you can see there are a lot more tributaries. So if we measure the lengths of all those stream channels and divide that by the area, we get a number for what's called the drainage density. And the reason that we collect all these numbers and things is because we want to be able to compare one drainage basin to another. Another characteristic we can look at is the shape of the drainage basin. We can look at the pattern that the rivers and the river and its tributaries make. So again, there are lots and lots of things that we could do. Some of them are quantitative, which means we can actually measure them and get a number, and some are much more descriptive or qualitative. So the drainage basin is kind of our unit of study, and And again, you can see this is a pretty big drainage basin, but within it there are all kinds of little drainage basins. We can pick any tributary and just look at the drainage basin for that. So many things we can measure there. If we zoom in, we can look at the channel. So the stream channel or the river channel has, again, things that we can measure and also things that we can observe. So the primary things to measure, or the first things, the obvious things to measure, would be the width and the depth of the channel, the velocity of the water within that channel, and then the discharge. And the discharge is the quantity of water. So it is the width times the depth times the velocity of the water. Now in our very simple picture here, that's a pretty simple and straightforward measurement. Most river channels do not have this nice uniform shape, so you need to measure the depth at multiple locations across the channel. And you also need to measure the velocity at different depths as you go across the channel. And when you do that, you can find out a lot about how a river works. For example, in a straight stream channel like the one we have on the picture here, the fastest water is typically near the middle, just below the surface. When you get near the bottom and the sides, you get a lot of turbulence, which tends to slow the water down. And if you're at the very top, the wind moving across the water can disturb the flow as well. So typically in a nice straight channel like this, our fastest water is in the middle, just below the surface. We will see that that is not as common as you might think. River channels bend, they move around, and as they take on different shapes, where the fastest water in will change as well. Some other things that we could measure on the channel is we could measure the slope of the channel. So how steep is it? That's something that we're going to do in lab. That's called the river gradient. So the slope of the channel is called the gradient. That's something to measure. There's another feature called the roughness. So this channel appears to have a pretty smooth bottom, but if you've looked at even a few river channels, you'll know some of them have rocks and boulders and stuff, very rough bottoms. Some of them have very smooth bottoms, and most channels are somewhere in between there. They're a mix. The roughness turns out is actually a little bit difficult to measure with a number. There is an important equation that we use in geology because knowing the roughness actually affects some other characteristics of the river. So when we want to do something like that, take a qualitative observation and turn it into a quantitative number that we could use in equations. In the case of roughness, there's actually a book that allows you to do that. It has pictures of different stream channel conditions, and it assigns a number to each of those based on research that's been done. So many things that we can measure in rivers to try to figure out what's going on. Now, for our purposes, we're going to do a little bit of this in lab. But one of the takeaways for our class, because we're kind of just getting into geology, is I'm not going to make you do a whole bunch with the numbers. You should, however, be aware that the information that we're going through from here on out is based on a lot of work, and a lot of it comes back to observation, collecting numbers, figuring out the width, the depth, the velocity, the area of the drainage basin, the relief ratio. All those things are included in the studies that give us the results that we're going to talk about. There will be a little bit of number stuff and some graphs because I think it's helpful to understand things. But I want you to have an idea that there's a lot of background that goes into this. People aren't just making things up because it sounds good. They're actually going out and collecting a lot of data and seeing if what sounds good and seems like it makes sense actually works with the observations that they make. So let's get into this and start with erosion. So this is a picture from your book. It talks about how the sediment is eroded. And it turns out there's actually a lot of physics involved in here. You have fluid dynamics. Don't worry about all that. We've got your conclusions right here on this slide. So clasts, or rock fragments, can be picked up by turbulence and the low pressure caused by moving water. The moving clasts can then collide with other clasts and objects and chip away. So that's how some additional weathering can occur. So once you start transporting sediments, they can knock into things and break them apart and weather them. And so you can see generally what's going on here is that as the water moves along, the water itself can pick up pieces, and then the pieces in the water can cause other pieces to break off and be picked up. You'll notice in the lower right, it also mentioned, because we're talking about water here, water can dissolve some of the minerals that are in the rock. It can also turn some of those minerals into clay minerals. So we've got chemical and physical weathering going on here that then results in sediment being picked up and removed, which is erosion. So our river can transport its sediment in 3 different ways. So we kind of group those ways into these 3 groups. These suspended materials tend to be the smaller materials. So anything that the river can pick up and carry along in the current is what we call suspended load. It's suspended above the bottom. The bed load is the material that's bigger. It's too big to be carried along in the water, and so it bounces or rolls along the bottom, and that is referred to as the bed load. So if you were to go out and take a look at the Illinois River, for example, the water is very muddy, and that mud is the suspended load. You'll notice on this diagram that suspended load can include silt and clay, which are the finest particles. If the water is going fast enough, it can include sand as well. The bed load tends to be bigger stuff like gravel, but sand sometimes is the bed load depending on the ability of the stream to carry materials. The bed load, it turns out, can be quite large. If you have the right conditions, a river can actually move some really, really large boulders. And we'll see the evidence of that in some pictures a little bit later on. So, and then the third thing here is the dissolved load. That's the stuff you don't see. So the bed load is moving along the bottom. The suspended load makes the water look muddy, but the dissolved load is just sitting there in the water. Even if you look at clear water, it probably has some material dissolved in it. So that's our 3 methods of transporting sediment. Now, when we start to take the sediment and put it together with some of the characteristics we measured, what we find is some information that we can then graph on exactly what's going on. And what these lines show is anything above the red line is in suspension. And you'll notice the faster the water, the larger the pieces of sediment that can be carried. So at high velocity, sand can be part of the suspended load. As the water slows down, its ability to carry the sand-sized material decreases. Anything above the blue line is bed load as long as it's below the red line. So you can see that's where sand is for a lot of these, for this kind of middle velocity range. And then, of course, if the water slows down enough, the sediment will be deposited. The part of this curve that's missing that's kind of interesting is in order to pick up clay, this curve actually goes back up. The water has to go fairly quick. Clay is kind of sticky, so to pick up clay, the water's got to go pretty fast. But once clay is in suspension, the water pretty much has to stop before the clay drops out, and the same goes for the silt. And so we will leave it at that, and then we're going to talk in more detail about some of the features we see in rivers on the next narrated PowerPoint.